So imagine you are rendering a massive digital city for like a blockbuster film.
Oh, yeah. The really heavy stuff.
Exactly. We're talking millions of buildings, cars, streetlights, trees. And if you literally just copy and paste a single 3D tree a million times, your studio servers they'll instantly crash from the memory overload.
Right, the system just can't handle it.
So how do modern digital pipelines cheat the system to make the impossible possible? That is exactly what we're figuring out today.
Yeah, we are going under the hood of a very specific, very foundational set of concepts today. We're really looking at how data is managed at a massive industrial scale.
Whether you are deep in the trenches prepping for a major certification or you are just insanely curious about the high-level architecture of 3D pipelines, today's deep dives is your ultimate shortcut.
Absolutely.
Specifically, we are tackling practice questions for the NCP-OUSD
Yeah.
exam.
The big one.
Yeah. Just to lay out the ground rules for you, the facts of the exam itself. It's a 120-minute test. It is delivered entirely in English, and you're looking at about 60 to 70 multiple choice questions.
And you need a 70% to pass, right?
Yep, 70% is the magic number. But our mission today isn't just to hand you an answer key.
No, definitely not. I mean, if you just memorize the letters, you will fail the moment a question is rephrased on the actual test.
Exactly.
Instead, we are going to rigorously evaluate every single option for these practice questions. We really want to understand the underlying logic, like why do these systems behave the way they do?
So let's reverse engineer the pipeline, starting with the rules of resolution and scale. Let's look at question 1, which focuses on composition strength. It asks...
Oh, this is a good one to start with.
Yeah, it's foundational. So it says, when resolving conflicts between different sources of data targeting the same primitive object, which opinion takes the absolute highest priority during the composition process?
And the op.
Right, so option A is opinions defined locally within the current layer stack of the active stage. Option B is opinions brought in through payload operations that are explicitly loaded.
Okay, got it.
Option C is opinions established inside a currently selected variation set. Or, option D, opinions inherited from a parent class definition.
So to solve this, we really have to look at what the question is testing, which is how the scene composition system resolves arguments.
Right.
Because when multiple files or layers are telling a single 3D object to do different things, like make it red, make it blue, make it bigger, someone has to win.
So somebody's got to be the boss.
Exactly. Let's look at the incorrect options first. So options B, C, and D, the payloads, variations, and inherited classes, they are all essential mechanisms for building a scene, but structurally, they are lower in priority.
Okay, let's unpack this. Before we crown option A as the winner, why are the others subordinate? Like, what pushes them down the ladder?
It's all because of where the data originates. Option D, an inherited class, well, that provides the baseline rules. It's totally foundational, right? And a payload, option B, is external data you've invited in. A variation, option C, is just a pre-offered choice. But option A, the locally authored opinion on the active stage, that is the artist's current workspace.
Ah, I see.
The system is designed to always defer to the direct local intent of the user.
So if we think of a 3D scene like a massive symphony orchestra, the local layer stack, which is option A, the correct answer is the local conductor standing right there on the podium.
Yes.
They have absolute veto power over everything else.
That is a perfect way to visualize it. Option D, the inherited class, is like the sheet music. Option B, the payloads, might be a guest soloist, but the local opinion is the conductor waving the baton.
Right, and if the conductor says, play this slower, it overrides the sheet music and the soloist.
Precisely. And this architecture is super crucial because it allows an artist to make targeted tweaks to a shot without having to permanently alter the source assets on the network.
So the local conductor wins. But how does that logic scale when we aren't dealing with one object, but millions, like that digital forest we talked about earlier?
That is where it gets really heavy.
Yeah. So let's look at question 2. This one's on point instancing. What is the primary architectural advantage of utilizing point-based instancing over native primitive instancing when building massive environments like forests or entire cities?
Okay, let's hear the choices.
Option A is it allows each individual instance to maintain unique hierarchical structures and children. Option B, it ensures that every instance is fully editable and can receive local overrides. Option C, it provides automatic level of detail generation for every scattered object without user input. Or option D, it significantly reduces memory overhead by processing instances as flat arrays of transformation matrices rather than individual scene graph objects.
Okay, so this gets right to the heart of the scalability problem. Let's just eliminate A and B right away.
Why is that?
Because options A and B actually describe features of native primitive instancing, not point instancing. Native instancing allows for unique hierarchies and local overrides, which, as we just established, is incredibly heavy on the system.
Oh, right, because of all that local data.
Exactly. And option C, automatic level of detail generation, well, that's a procedural generation tool. It's not an inherent architectural feature of instancing.
Which leaves us with option D. But I have to ask, if I am building a massive forest, why can't I just duplicate the trees?
Just copy-paste.
Yeah, copy-paste over and over. Why do we need this specialized point instancing system at all?
What's fascinating here is the sheer math of the memory overhead. A standard scene graph hierarchy is a really complex tree of data. It contains geometry, shading materials, bounding boxes, metadata.
It's a lot of stuff.
A ton of stuff. If you copy and paste a tree 1,000,000 times, you are forcing the computer to clone and track that massive data structure 1,000,000 times. Oh, wow. So it's like carrying the complete architectural blueprints, plumbing schematics, and wiring diagrams for 1,000,000 houses, when all you actually needed was a single map showing where the identical houses go.
Yes, exactly. Point instancing, which is option D, replaces those full hierarchies with incredibly lightweight flat arrays.
Just flat lists of numbers, basically.
Basically, yeah. The system holds the heavy data for the tree exactly once in memory. Then, it uses a flat array of transformation matrices, basically just X, Y, Z coordinates that say, draw this one tree blueprint here, here, and here. It radically reduces the memory footprint.
So we can instance millions of trees mathematically. But wait, how does the software actually locate the original blueprint file on the studio's massive hard drives to begin with?
Now we're moving into resolution.
Right. That brings us to question 3, asset resolution systems. This one asks for 2 answers, by the way.
Okay, good to note.
Which of the following capabilities represent the core responsibilities of a custom asset resolution system implemented within a studio pipeline? Choose 2.
Let's hear them. Option A, translating logical uniform resource identifiers into physical storage locations. Option B, automatically generating proxy geometry for extremely heavy character assets.
Yeah.
Option C, handling version control logic to fetch specific iterations of an asset from a database. And option D, converting incompatible proprietary geometry formats into native framework definitions.
All right, since we need 2 correct answers, let's weed out the distractors by really understanding what an asset resolver actually does.
Right.
It is a librarian, not a creator. Option B suggests it generates proxy geometry. Option D suggests it converts file formats.
And it doesn't do that.
No, those are heavy, computationally expensive tasks meant for geometry processors or file translators. If an asset resolver had to convert files, the whole pipeline would just grind to a halt trying to locate a path.
So an asset resolver is strictly about finding things.
Exactly.
Which means the correct answers have to be A and C, translating identifiers into storage locations and handling version control.
Yes. If we connect this to the bigger picture, maintaining consistency across a studio's server is a nightmare if files move around.
Oh, I bet. Broken links everywhere.
Right. An artist's tool shouldn't need to know the literal server path. It just asks for a logical identifier, like hierarchist.
Okay.
The asset resolver takes that abstract request, applies version control logic, which is option C, and translates it into the literal physical storage location, like the Z drive, project folder, version 14. That's option A.
It finds the book so you don't have to memorize the exact shelf number.
Exactly.
Okay, so once the system resolves those assets and builds this massive complex scene, what happens when we need to package it up and send it to an external vendor who doesn't have access to our library?
That's where flattening comes in.
Right. Question 4 deals with flattening. What is the fundamental result of executing a flatten operation on a highly complex composed scene before delivering it to an external vendor?
Okay, let's look at the options.
Option A is it converts all 3-dimensional geometry into 2-dimensional projection planes for faster review. Option B, it collapses all composition operations and sublayers into a single monolithic file containing only local opinions.
Right.
Option C, it compresses the internal memory footprint without altering the external file structure. And option D, it strips away all animation data to provide a completely static reference frame for the recipient.
Well, options A, C, and D are honestly just fabricated to sound technical, but they're entirely wrong.
So it's not 2D projection planes.
No, flattening has nothing to do with rendering 2D planes, doing internal memory zipping, or stripping out your animation. The correct answer is B.
So what does this all mean in practice? Is this essentially like merging all the layers of a complex Photoshop document before emailing it as a flat JPEG?
That is the exact perfect analogy. When you are working internally, your scene is incredibly complex. It has payloads, inherited classes, variations, references pointing to 100 different network drives.
Mhm.
But an external vendor, they don't have access to your internal pipeline infrastructure or those upstream network dependencies.
So if you send them the working file, it's just going to be a million broken links for them.
Exactly.
But this sounds like a one-way street. Once you flatten it to a JPEG, you can't unflatten it to, like, tweak the lighting on layer 4.
Right. It is completely destructive to the structure. When you execute a flatten operation, the system evaluates all those complex composition arcs we discussed earlier, decides who wins every argument, and bakes the final result down into one single monolithic file.
Wow.
The entire dependency structure is just gone, leaving only the final resolved local opinions.
Let's pivot slightly to navigation. Before we even get to flattening a scene, our software tools need to be able to navigate these massive hierarchies without freezing up.
Right, which is no small feat.
Definitely not. Question 5 explores traversal rules. When writing a tool to iterate through the entire hierarchy of a scene graph, which primitives are intentionally skipped by the default traversal rules to ensure optimal performance and prevent errors.
Okay, what are our choices?
Option A, primitives that have custom rendering materials bound to them. Option B, primitives that currently lack geometric data or bounding boxes. Option C, primitives that are marked as inactive or are currently unloaded from memory. Or option D, primitives that are deeply nested beyond 3 levels of hierarchy.
The key here is really understanding the phrase default traversal rules.
Okay.
A software tool walking through a scene graph doesn't inherently care about custom materials, so option A is out. Doesn't care if a bounding box is missing because, honestly, it might be traversing the graph specifically to calculate that missing box.
Oh, that makes sense. So B is wrong.
Right. And it certainly doesn't arbitrarily give up after 3 levels of nesting. I mean, production scenes have dozens of nested levels, so option D is incorrect.
Which leaves option C, primitives that are marked as inactive or unloaded. I mean, it sounds obvious when you say it out loud, but mechanically, why is skipping them so critical for performance?
Because if a primitive is inactive or unloaded, an artist has explicitly told the system, do not include this in the current compose stage.
Right.
If a custom tool ignores that and forces the system to wake up and process gigabytes of intentionally disabled content, you lose stability immediately. The default behavior is to just walk right past them to conserve compute power.
Keep the machine running smoothly. I like it. Okay, so the software successfully navigates the active scene graph. How do we actually get it to draw the pixels on the screen?
Now we're talking about rendering delegates.
Exactly. Question 6 covers rendering delegates. Within the modular visualization architecture, what are the primary roles of the rendering delegate component? Choose 2.
Okay, 2 answers here.
Option A, parsing the core scene files directly from the local storage disk. Option B, consuming the unified rendering index to generate the final pixels for the viewer. Option C, providing the mathematical calculations for rigid body physics simulations. Or option D, bridging the standardized rendering data to a specific proprietary rendering engine.
Well, let's just drop A and C immediately. Parsing files from a disk is a file format plugin's job, and calculating rigid body physics, that's a physics engine's job.
Right, makes sense.
A rendering delegate doesn't do file I/O or physics. The correct answers are B and D.
Wait, let me push back on B and D for a second. If it bridges data to a proprietary rendering engine, does the rendering delegate itself actually render the image?
No, and that's a crucial distinction. The delegate is purely a translator.
Oh, okay.
If we connect this to the bigger picture, a modern visualization architecture creates one unified index of the 3D scene. But a studio might use 3 different renderers, like a fast rasterizer for real-time viewport preview and a computationally heavy ray tracer for the final film output.
Oh, I see.
The rendering delegate just sits in the middle. It consumes the unified index, which is option B, and translates that standardized data into the specific proprietary language that the chosen rendering engine understands, which is option D. It passes the instructions, but the engine does the heavy lifting.
Okay, so we've built the space, traversed it, and rendered it. What happens when we add the dimension of time?
Oh, animation.
Yeah. Question 7 deals with temporal interpolation. How does the core data system handle queries for a specific animated value that falls exactly between two authored temporal keyframes?
Let's hear the options.
Option A. It automatically calculates a linear interpolation between the surrounding authored values. Option B. It strictly returns the value of the newest preceding keyframe to avoid mathematical rounding errors.
Okay.
Option C. It queries the rendering engine to calculate a complex curve approximation based on neighbors. Or Option D. It returns an error state demanding explicit user authoring for that specific frame.
So let's dismiss B, C, and D purely based on efficiency. The system doesn't just statically hold the previous frame like a stop-motion film.
Right.
It doesn't bog down the rendering engine with complex spline curve math just for basic data retrieval. And it definitely doesn't throw an error demanding you manually author every single frame. Option A is the correct answer. Linear interpolation.
See, here's where it gets really interesting to me. This is entirely about storage efficiency, isn't it?
Absolutely. If a car is at position 0 on frame 1 and position 100 on frame 10, you don't want to save the explicit position data for frames 2 through 9 on your network.
That would just be a massive waste of space.
It's a huge waste of space. If a tool asks the system, hey, where's the car on frame 5? Linear interpolation just splits the difference dynamically and calculates position 50. It allows for smooth, continuous motion without the bloated storage cost.
Now, to keep all this spatial and temporal data organized across an entire studio, you need strict architectural blueprints. That brings us to question 8. Typed schemas.
Schemas are so important.
When designing a custom type schema for a proprietary pipeline, where must the default fallback values for its attributes be strictly defined to ensure they are globally recognized without requiring local overrides?
Okay, let's hear the choices.
Option A. Inside the root layer metadata of every individual scene that uses the new schema. Option B. Within the active memory cache immediately after the creative application launches. Option C. In the generated plugin registry files created during the schema compilation process. Or Option D, hard-coded directly into the user interface scripts that the environmental artists use.
The key word in this question is globally recognized.
Okay.
Let's look at why A, B, and D completely fail that test.
Okay.
If you put fallbacks in an individual scene's metadata option A, well, no other scene on the network knows about them. If you hard-code them into a UI script option D, only the artists using that specific interface tool get the defaults.
Oh, right. It's too isolated.
Exactly. And option B, the active memory cache, is volatile. I mean, it clears out when you close the program.
Which leaves option C, the generated plugin registry files.
Yes. When a pipeline developer compiles a new schema, it generates core registry files. This acts as a centralized global dictionary for the entire pipeline.
So it's always there.
Exactly. If an attribute is missing a local value anywhere in the studio, the software checks the plugin registry and instantly knows the fallback default. It provides this really ironclad safety net.
So schemas give us our strict global defaults. But, pipelines aren't perfectly rigid. Artists need to make creative variations. If the schema sets the rule, how do we safely break it?
Variations.
Right. Let's look at question 9. Variant selections. Which of the following methods are valid ways to specify which variation should be active within a defined set of variations? Choose 3.
Okay, 3 valid methods here.
Option A is authoring a specific selection locally on the primitive object that holds the variations. Option B, setting a global default fallback selection in the system plugin configuration. Option C, relying on the alphabetical order of the variation names to automatically pick the first one. Option D, inheriting a selection choice from a stronger composition operation higher up in the hierarchy.
Right.
Or Option E, using a random number generator node within the geometry definition rules.
Since we need 3 valid methods, let's just identify the 2 that would cause absolute chaos in production.
Chaos is bad.
Yes. Option C, relying on alphabetical order, is disastrous. Imagine an artist names variations damaged and pristine. Alphabetically damaged is default.
Okay.
If someone renames it to Z-damaged to sort it at the bottom of a list, suddenly every prof in a 10,000 frame render flips to pristine. You can't base active pipeline assets on simple spelling.
Yeah, that sounds awful.
Yeah.
And Option E, using a random number generator, that violates the need for predictable behavior. You don't want your props randomly changing color every time you open the file.
Precisely. Which leaves A, B, and D as our correct answers. You can author a choice locally right on the object, which is option A. If no local choice is made, you can let it inherit a selection from a stronger composition operation, kind of like our conductor from question 1, which is option D. Or if absolutely nothing is authored anywhere, it relies on the global default fallback from the plugin configuration, which is option B.
We have finally reached part 5, the foundational bedrock.
The deepest part, the dive.
Exactly. We've scaled up to massive forests, navigated rendering, track time, and broken rules with variations.
Okay.
Let's strip away all of that complexity and look at the absolute basic atoms of this data model. Question 10. Relationships versus attributes.
Okay.
What is the foundational difference between a relationship and an attribute when designing data models for a scene?
And the options.
Option A. Relationships store heavy geometric arrays while attributes only store single Boolean values. Option B. Relationships are evaluated first during rendering, while attributes are evaluated last. Option C. Relationships can only exist at the root level of a document, while attributes exist on child objects. Or option D. Relationships act as pointers to other objects within the hierarchy, while attributes contain actual typed data values.
Well, options A, B, and C are entirely nonsensical rules. Relationships don't store heavy geometry, they aren't bound to a strict rendering timeline, and they certainly aren't restricted to the root level.
So what's the real difference?
The structural distinction here is purely about the type of data being managed. Option D is the correct answer.
To make sure this is crystal clear for you listening, attributes hold the actual stuff, the typed data. An attribute is the number 5, it is the color red, it is a mathematical string.
Right.
Relationships, on the other hand, don't hold any actual data themselves. They are just the red string connecting the photos on a detective's corkboard. They are lightweight pointers that say, hey, go look at that object over there.
Exactly. Relationships are the structural references. Bindings, dependencies, material assignments that wire the disparate pieces of the scene graph together without duplicating the heavy data.
Thank you for joining us on this deep dive. Remember, memorizing A, B, C, or D might get you through a quiz, but mastering these underlying mechanisms, the why and the how, that is the true key to unlocking pipeline architecture. Catch you next time.